Hi, I'm Willow Chandarina with the Amazon Elastic File System Product Management team. We're going to be talking about persistent storage for containers using Amazon EFS. We're going to start by talking about why you might want persistent storage for your containers. Then we're going to walk through some best practices around identity and security for those containers, no matter how you're launching them. Then we're going to go through some how-to on how to get started with ECS, and then how to get started with EKS before walking through some more best practices. Let's start out by talking about why persistent storage for containers. As we talk to customers who are containerizing more of their applications, generally we find that there's one of two patterns why they might want persistent storage for those containers. The first one is that they're deploying applications that need to be stateful or long-running, and they want to use storage to make sure that those applications are resilient to any sort of application or infrastructure failure. So by storing data or state outside of the container, it means that they can be resilient to those failures. The other reason for persistent storage is so that those containers can share data, either with other containers of the same application or with containers of other microservices in the overall architecture. Let's walk through some examples. So with developer tools, Jenkins benefits from shared storage because Jenkins can launch scale-out CI/CD jobs around a shared view of data in order to get those jobs done quickly. With Jira, attachments to bug reports can be stored in persistent storage to make sure that those systems are resilient to failure and your developers don't lose any time if those applications need to be rescheduled in some other part of the infrastructure. Web and content management systems benefit from both the persistent and the shared nature of shared storage. So the persistence is handy to make sure that any content you have or user uploads is always going to be available and durable. And the shared nature helps you scale out when more demand comes on your systems and scale back down in times of less demand so that you can save cost. Machine learning and data science is a common use case for persistent storage, both for data science tooling and also for training jobs. So on the training jobs, you often want to make sure that you can scale out those training jobs across multiple containers in order to get the jobs done quickly, but you need all of those containers to be working on a single view of data, which is your shared data in your persistent file system. For tooling, oftentimes you want data scientists to have their own tooling, such as their notebook server, so that they can customize it and have everything that they need. But for those data scientists to be effective, they need to have a shared view of data with other data scientists so that they can share their models, share their data sets, and make sure they can collaborate as a team. Often when companies try to get persistent storage with containers using existing or legacy storage technologies, they run into the same kind of challenges that they had that have them running to containers in the first place, such as lack of scalability. So having to always running out of space in their application volumes, having to deploy new ones, migrate data between them. Lack of agility. So this comes from application developers always having to talk to someone on the storage side to provision something before they can deploy an application. And just overall administrative overhead of dealing with non-managed solutions. So the patching, the upgrades, monitoring management, all of that. And it was all those challenges that led us to introduce Amazon Elastic File System back in 2016. Amazon EFS is a shared file system that is cloud native, highly reliable, and cost optimized. So it's cloud native in that it's something that we've built natively for the cloud. So it's something that's fully elastic and pay as you go and integrated with all of the other services you might want to use in the AWS portfolio. One way you can think of this is it's serverless storage because it's something that you don't have to think about, pay as you go, fully elastic, nothing to manage. It's highly reliable because all data that you write to EFS is available from all availability zones within a region, And that data is actually durably written to at least 3 availability zones within each region. So you can make sure that that data is always available, and it'll in turn keep your applications highly available as well. And it's cost optimized. It's cost optimized not only because of the elastic pay-as-you-go nature, but also because we offer 2 storage classes for your data. One is the EFS standard storage class, which is high performance flash tier, as well as a infrequent access storage class, which is 92% lower cost. And we automatically move data transparently between the 2 to give you the lowest blended storage cost possible for your workload. When you put together Amazon EFS with the AWS container services, you get several benefits just because of how well these things work together. So first is the simplicity. So it's the simplicity of having a fully managed container orchestrator with a fully managed file system. It makes it really easy for you to get started and run your applications without worrying about managing infrastructure. Even further, the way that we've done this integration is that all of the EFS configuration is at the application manifest or at the task definition layer, which means developers can simply state what they want for what kind of storage they want their applications to have, and have the infrastructure provided for them rather than manage individual instances. This is highly available and durable. I mentioned the availability and durability of EFS, but the thing to realize is EFS is a regional service, as is Amazon Elastic Container Service and Elastic Kubernetes Service, ECS and EKS. And when you combine all of these regional services together, what it means is you don't have to worry about architecting your applications to be multi-availability zone aware and have failover between those availability zones, because the frameworks will take care of it and EFS will be available wherever your application is launched. Next, we have the elasticity benefit of using Elastic Container Services with Elastic File System. So now you have serverless compute and you have serverless storage, which go really well together. And it's not always a matter of them scaling together. Sometimes that's important, but also their ability to scale separately. So you can scale in and out your compute as you have more users using the system, and you scale in and out your storage as you need to store more data. So you're always optimizing for both your compute and your storage cost. Last is these solutions have been integrated together in such a way that all of the best practices of security are possible. So you can encrypt your data, you can authorize access from your containers into your file system, and do so in a way that's very simple. We're going to talk in just a minute about identity and security and how you actually make these things work together. Let's just talk for a minute about exactly what's supported today so that you know what you can get started with now. So this was recorded in July 2020. So you know that on AWS, you can either deploy your containers into Elastic Container Service or Elastic Kubernetes Service. These are the 2 container orchestrator services that we have. Both of those, in turn, can launch those containers either onto EC2 instances that are part of your cluster or into Fargate, which is a completely managed service, so you don't have to manage any of the underlying infrastructure for where those containers run. So all of these are supported with each other right now. Now, with regard to EFS, today EFS is supported with ECS in both modes, both the EC2 and Fargate launch mode. With EKS, currently EFS is supported with the EC2 launch mode. It's not yet supported with EKS launch mode, but that's something that is coming soon. So keep an eye on that in the public GitHub page. Let's walk through some case studies of how customers are already having success with EFS and container services before we walk into some of the details. So Caltech uses EFS and container services in order to quickly spin up new applications and new websites as needed. So the problem that they had before was they just weren't able to move fast enough. Whenever they were spinning up a new website, it would take days. Once they started adopting our container services with EFS, they were able to handle a request to spin up a new funding website within hours, which was an enormous improvement to them. Next, T-Mobile is using container services and EFS to help them scale up and down their applications much easier. So the challenge they had was they couldn't move fast enough in scaling their applications for user demand. So more users were using their services, and they needed to be able to scale out and meet that need fast. With container services, they can easily add containers to handle that load now. And many of those applications required persistent storage, either because they were long-running applications or because they needed shared storage. And what they did to make sure that their development teams were agile about creating these solutions was they made it fully self-service for their application developers to create and attach EFS file systems to their containers. So now they can spin up new services really quickly and achieve their scale goals that they originally set out to do. Next, Discover Financial have a data science team that was using an on-premises platform. They migrated that platform into AWS in order to take advantage of the additional capacity and being able to elastically scale. And they're now getting the elasticity and fully managed benefits of using both Elastic Kubernetes Service and EFS. And what they've actually deployed is a full data science environment called Air9, which enables each of their data scientists to have their own environment with notebooks and other tools. Each of their data scientists have their own home directory that's backed by EFS, and each of their teams has a team directory backed by EFS. So it's really simple for their data scientists to get access to the data they need while having their own custom environment. And everything is fully elastic, so they can move very quickly. Similarly, a company called Faculty builds and provides ML solutions to companies. They've built a platform that uses container services and EFS so that, again, data scientists can have home directories, they can have project directories, but all the data scientists have their own tooling and they can move quite quickly. So this is a very common use case for customers who are doing data science with EFS using containers. So now that we've walked through that, let's talk about some considerations for identity and security when you're using containers with EFS. And we're going to start by just talking about what are the goals of identity and security with this. What are you trying to get done? The first thing that most people are trying to do is make sure that a particular file system can be accessed by the container that needs it, but not the containers or applications that don't. So we see here a container can and does have access to a file system, while another container should not and does not have access. Next, once a container gets access to the file system, it should only have access to the data that it needs. So we see here that this container mounted the file system, catted a file that belongs to it, and got a success, this is my file. The cat operation succeeded, while it tried to cat a file that belonged to another application and got a permission denied error. So now I'm going to walk through how you can actually achieve this using EFS. Now for the first goal of making sure that a file system is only mountable from the containers that should be able to access it, we're going to use IAM. So here what we see is we have a task running in Elastic Container Service. That task has a role associated with it called the task role. And when that task mounts EFS, the task role is passed to EFS, and EFS checks that against an IAM policy in order to figure out whether that mount should be successful or rejected. And this is super easy to set up. So you can set this up either by attaching an IAM policy to the role itself. So this is a policy that says this particular role is allowed to do this action on this particular file system. Or you can do it from the file system's point of view. So you can apply a resource policy to the file system that says this role or these roles are allowed to perform this action on this file system. You can use both of these together. You can use one or the other. They'll both be taken into account whenever your application is mounting the file system. From the ECS side, this is super easy to set up. All you have to do is associate a task role with your task, and then check the box in your volume definition for Enable IAM Authorization. Let's talk about the actual actions that you are giving access to using IAM. So first, there is an action called client mount. Client mount means that anyone who is given permission to perform this action can mount the file system, as the name suggests, and has read-only access to the data in that file system. It will not be able to write to the file system, as you can see in the picture. So here we have given principal star access to client mount, which means any IAM role, even anonymous ones, are allowed to mount the file system and read data but not write. If you want your application to be able to write to the file system, you can add a permission called client write. So client mount plus client write means anyone given access to that can mount and write, and obviously read. What it doesn't give access to is the ability to read or write using the root identity. So in NFS or just file system space, every operation you do has a particular user ID and group ID associated with it, and the ID of 0 means root or administrative access to the file system. In most cases, you actually don't want to give administrative access to your apps because it means they can read and write, delete anything in the file system, not just what you've given access to. So if you only give client mount and client write, what's going to happen is any operation that is non-root is going to be successful. But if the client tries to do a write using user ID of 0 or root, it will be squashed to a well-known user ID of 65535, which means most of those operations are going to fail. And last, if you want your application to have full administrative root access to your file system, you can add a third permission, which is called client root access. So when you give all three of these permissions, your applications can read, write, and do both of those as root. Now let's talk about the second goal, which is how do you make sure that once an application mounts a file system, it's able to only access the files that it should access and not any others. So what we have here is a ECS task, a single container within that task, and that task has a task identity of an IAM role. It's mounting a file system, and there's already data inside that file system. The data inside that file system is a directory called Bob Home, owned by Bob, a directory called Sally Home, owned by Sally, and then a shared directory called BI Shared. Now, what we see here is that the container image that's part of this task has already been built, and at build time, the application was built to run as user root and group root. Remember, that's UID 0, group ID 0. Let's see what happens if you do no other configuration and that container tries to read and write from the file system. We see that it can do a read to Bob's directory with user ID 0. And what we see here is that by default, the POSIX identity, the user ID and group ID, come from the container image, not the runtime of the tasker pod, which is really important to keep in mind because a lot of times what you're going to be doing is running containers you find in Docker Hub, running containers someone else in your company built. So this is an important thing to keep in mind. The container identity is from the container's perspective, not the runtime of the pod or the task or whatever the entity is that's running that container. But there's a fix for this. There's a way to control that. And the way to control that is by using EFS access points. EFS access points are application-specific entry points into your file system that allow you to control the identity of the underlying application. So let's look at an EFS access point definition and see what sort of things that you can configure in there. So here we have an access point. That access point is associated with a particular file system ID, and there is a POSIX user that you configure. So the POSIX user is the user ID and the group ID and any other secondary group IDs that become associated with any application that uses that file system. So this is, think of it as an override for these fields for anyone that comes through this door. There's another thing that this does too, because most of the time that you are setting up a new application on a file system, you're going to want a space for that application to write. You're going to want a new directory. You can have your access point create that directory on behalf of your application with the permissions you want, so that you don't need to use any other systems to deploy directory and permissions to your file system. So just to recap, there's two key benefits that you get by using EFS access points. First is you're enforcing the file system identity of a particular application rather than trusting the identity of the container as it was built. Next is you can create application-specific directory and permissions so that you don't have to create an EC2 instance, mount your file system, create directory, change mod it to the permissions and other things before you can run your app. You can just do it in one step and then run your app directly. Let's just walk through a visual example of how access points work. So we see here we have an application that's mounting the file system through the access point that we just created. It's the same application as earlier, so it's running a container that was built to run as root, so it's going to be trying to perform EFS file system operations as user ID 0 or root. When it passes through the access point is going to rewrite those operations as user ID 123, just like we'd configured it to. So we see here we're able to control exactly what identity we use. Now, the next thing you may be wondering is, how do I make sure that a particular application is going to use a particular access point? You can use IAM for that. So now we're putting both of these concepts together. Here, and this isn't a literal policy, look at the documentation before you write your policy. But the gist of it is, you configure your file system policy to say this particular role is allowed to mount this file system, but only if it uses this particular access point. So that prevents this application from using someone else's access point or mounting the file system directly. Let's talk best practices for IAM and access points. So first, use access points. They're going to make your life a lot easier and take away a lot of the unpredictability that would come in trusting whatever the identity of the container image is. Next, use IAM authorization. This is the simplest way to set up security for your file system, because the alternative is to use network-based security groups in order to control access to your file system. And security groups are based on IP addresses. You don't always know what IP address your container is going to have when it gets launched. So it's a little bit tricky to use those. But when you use IAM and you link specific roles with specific file systems, you can set everything up ahead of time and ensure that the right application has access to the right apps, to the right file systems. Last, enable encryption at rest and encryption at motion. Both are just checkboxes. There's no downside in turning on either of them, no extra cost, no performance hit, nothing. So check the boxes and just make sure that you're secure by default. So let's walk through some how-tos. How do you get started with using EFS for ECS and then using ECS for EKS? So we announced in early April that we had native deep integration between ECS and Fargate with EFS. Three key benefits came out of this integration. First is it's a lot simpler to use now than it was in the past. So now all of the EFS configuration is done in the ECS task definition, which means developers can just indicate what file system they want to connect to and have the infrastructure take care of the rest. No more messing with underlying instances and referencing default mounts and things like that you may have been doing before. Most exciting is that now you can use it with Fargate. So now you can have serverless compute with your serverless storage and simply deploy applications and have to manage close to zero infrastructure. And last, we've integrated this with IAM and access points, the security features that I just talked about, so it's really easy to be secure out of the box. So here's a visual example of how it works. We see here that we have our task. In our task, we have a couple of containers, and it references the file system through the EFS volume configuration component of the task definition. Once you've configured that, you can launch that task either on EC2 or Fargate. If you're in the ECS console, it's easy to get started. Within your volume definition, within your container definition, there's a button you can click for Add Volumes. And within Add Volume, you select EFS under volume type, and all of these choices appear. So you can name it, You can have a drop-down box for which file system ID you want to connect to, which access point you want to connect to, and then it's just checkboxes for whether you want to enable encryption in transit or IAM authorization. So check those, hit add. Once your volume is part of your task definition, you can then go into your container, and inside your container there's a part called mount points. You reference the name that you gave your volume in the last dialog, and then you say what path within the container you want to mount into. And that's it. Then you click OK, you launch your container, and then it connects to EFS. Here's what the JSON in the background would look like if you use this, or if you want to configure it yourself. So we see on the bottom here, there's volumes, and within volumes, you say what your file system ID is, and you make all the other choices. And then you take that name and reference it up above with your mount points. And it's really as simple as that. You can use this with the CLI, API, CloudFormation, however else that you're launching your application. Let's talk about how to use this from EKS now, using the CSI driver. So with EKS, the way that EFS is implemented is using something called the CSI Container Storage Interface framework, of which there is a CSI driver. So the CSI framework is something that allows anyone who provides storage to write a driver and make it easy for developers to get access to storage without having to know any of the details about the storage itself. So there's the container storage interface, which is the framework. There's an EFS CSI driver that we've written and made available. And once you have both of those, there's these other concepts called storage class, persistent volume, and persistent volume claim. So the storage class is an administrator-defined class of storage that is the interface between what the storage provider is and what developers request access to. We'll see an example of this in a second. And then the actual thing that gets allocated is called a persistent volume, which is loosely associated with a file system on the back end. So let's walk through an example of how the process flow would work. So when you first set up your Kubernetes or EKS cluster, the administrator goes in and sets up the drivers and connects to the storage. So first they create a storage class, which is just a name that's associated with a particular type of storage that you're making available. And then within that storage class, you launch multiple persistent volumes. And each of those can point to a different file system, or you can have multiple persistent volumes pointing to the same file system just under different access points. Once those persistent volumes are created, they become a pool of storage resources that a developer can get access to. So the next thing that happens is a developer comes along and wants to launch an application. They create a persistent volume claim that asks for a particular storage class. So the developer doesn't claim a file system directly. They simply say, I want a volume from the storage class of EFS. And Kubernetes will match them to a available persistent volume from the pool, and then allow them to connect that to their pod when they launch it. Setting this up is pretty simple. Here's some sample YAMLs of how you would define all of this. So when you create the storage class, it's basically nothing more than saying which driver to use for this. In this case, it's the EFS CSI driver. You then create your persistent volume. That's where you actually say this persistent volume is attached to this particular file system and access point. Then the user or developer comes around and creates the persistent volume claim referencing only the storage class. And Kubernetes is going to pick an available persistent volume and hand it back to the user that they can then launch their pod referencing, and now their application is running in a container using EFS for persistent storage. So now let's wrap up by looking at some other best practices around performance, cost, and ingesting your data. Let's start with performance. In case you missed it, recently we at EFS announced a significant increase to file system operations per second, or IOPS. So we announced a 400% increase in read operations on general purpose mode file systems, which is a huge improvement. to what it was before. So our recommendation is to use general purpose file systems for most of the applications that you are creating. It has the lowest per operation latency, which means it's going to be most appropriate for the things that you're going to be running in containers. The other mode, max IO, might be relevant to you if you are launching scale-out applications, so massively scale-out analytics or ML applications, where you're looking for the most aggregate IOPS, 100K IOPS or more. Next, when you configure the throughput of your file system, there's two throughput modes you can choose from. There's bursting throughput mode, and then there's provision throughput mode. In bursting throughput mode, we're going to give you an amount of throughput that's based on the amount of data that you're storing in your file system. With provision, you just tell us how much throughput you want and we give it to you. Now, if you're launching a brand new container, you may not have data in your file system yet, but you probably want throughput so that you can start handling your users or start ingesting data. So what I would recommend is that you start with provision throughput so that you make sure that you always have enough throughput for the application. Now, the good thing about provision throughput is you never pay for more than you would have gotten with your entitlement. So for instance, if you would have been entitled to 10 megabytes per second based on the amount of data that you had stored, and you provision 20 megabytes per second, you only pay for the incremental 10. You don't pay for all 20. But the other benefit of that is now if you ingest a lot more data and now you're entitled to 30 megabytes per second, you get the max of the two. So now we'll give you 30 rather than the 20 that you configured. So it's a good idea to configure the minimum throughput that you need through provision throughput, and then let your storage grow and potentially override that with even more throughput. Last, set up CloudWatch and monitor your throughput, monitor your IOPS, monitor your burst credits, just to make sure that you've configured these things correctly and you have exactly what you need for your application. A question we get sometimes is, for my app, should I use Elastic File System or should I use EBS, Elastic Block Store? The easy way to tell the difference between whether you need one or the other is, do you need to share data between your application and other applications? If the answer to that is yes, you want Elastic File System because EFS is a shared file system. EBS is something that you attach to a single application. Another reason you might want to use EFS is if you want to have access to your data no matter what availability zone you're in within your region. This could be useful if you're taking advantage of spot pricing, for instance. On the other hand, if you're launching a transactional application like a database, you may want to use EBS because most databases don't need to share data and they need very low per operation latency. And you can benefit from the fact that all of your data is right next to your application with EBS. You may also want EBS if your application relies on point-in-time snapshots, which are not yet available with EFS. You may also consider Amazon FSx for Lustre if you're running an application that is highly scale-out, needs tens of gigabytes per second of throughput. So you're doing high-performance computing or simulations or rendering or something like that. That's another option for you. Let's talk about how to optimize cost with EFS. I mentioned earlier that EFS has two storage classes, EFS Standard and EFS Infrequent Access, and a feature called Lifecycle Management, which automatically moves data between the two based on access patterns. So when you configure Lifecycle Management, you tell EFS whether you want to automatically move data after 7 days, 14 days, 30, or up to 90 days of inactivity, or time since the last time you read or wrote that file. Based on that, we are going to individually move files from EFS Standard to EFS Infrequent Access completely transparently to you, your users, and your applications. Which means when you do an LS, you'll see all of your files, whether they're in standard or infrequent access, and you can still read and write that data as if it's all in the single file system, which it is. The only thing is, once data moves to IA, you're paying 92% less for that data. So if you think about this in terms of blended storage cost, oftentimes our customers get more than 80% lower storage costs by turning on infrequent access because so much of their data has been sitting around not being actively accessed, but they don't they have to hold on to it in case their application needs it. So recommend checking that out and turning it on. Next, let's talk about backups. So nobody wants to be in a position where they launch a new container and that container goes into their existing file system and deletes a file that it shouldn't. A really easy way to avoid this is by using the AWS service AWS Backup. With AWS Backup, you can simply configure a backup policy that can apply to one or many file systems that will, you can say a policy such as back up your file system every day, keep those backups for a week, back up your file system each week and keep it for a month. And AWS Backup will manage everything for you. And if the time comes where you have to restore any of your data, you can either restore the entire file system or a single file, a single directory. It's up to you. Next, you may be wondering, how do you get started with this? How do you get existing applications moved into AWS so that you can take advantage of EFS and container services? Good news is we have a service for this called AWS Data Sync. So if you have an on-premises environment, you can deploy an AWS Data Sync agent in your on-premises network. And that agent is going to connect to your existing storage. And then it will connect to the AWS managed Data Sync service in AWS. And then you can configure either a one-time or incremental synchronization of data from on-premises into the cloud. Once the data is moved, that means now your applications can move simply as well. In some cases, customers have set it up so that once they move their data over the first time, they still have some on-premises applications connecting through AWS Direct Connect to Elastic File System. So if you're looking to learn more about this, we have a bunch of resources on our website that can help you. So Massimo Referre, a container developer advocate, wrote a 3-part blog series on Developer's Guide to Amazon EFS with ECS and Fargate. I'd recommend you check that out. It talks about why you'd want to do it, talks a lot about the theory, and then it walks through a specific example of how to actually do it, complete with code snippets. Next, on YouTube, we have a great demo video that shows pictorially how all these connections work, and then it shows a sample application that utilizes EFS for persistent container storage. So it's a really good watch, highly produced. I'd recommend you check it out. And that's all I've got for today. Thank you so much for joining me. Happy containerizing.